Welcome to our introduction of capacitors in circuits. We'll first do a quick review of capacitors. Capacitors are devices that are used to store electrical charge and energy. Here are a few examples of capacitors that are found in typical circuits. In general, a capacitor consists of two equal and opposite charged conductors. The potential difference between the two capacitor plates, V, is directly proportional to the charge Q on each of these plates. If you were to say double the electric potential across these two plates, then you would find that you would have double the amount of charge. The capacitance C of the capacitor is equal to the ratio of the charge divided by the voltage V. The capacitance is a measure of a capacitor's ability to store charge. The SI units of capacitance are in farads. 1 farad is equivalent to 1 coulomb per volt. However, typically in our problems we won't see capacitance of 1 farad. We'll likely see units of microfarads, which is equivalent to 1 times 10 to the power negative 6 farads, or you might see picofarads, which is equivalent to 1 times 10 to the power negative 12 farads. Since capacitance is the ability of an object to store electrical charge, you might find this analogy to be helpful. You can think of charge like cotton balls, voltage like pressure, the battery like a pump, and capacitance is that ability of a jar and holding something like the cotton balls. So the capacitor would represent the jar, and capacitance would be how big that jar is. So if you were to apply more pressure, hence higher voltage, you'd be able to stuff in more charge or cotton balls into that jar, and hence you'd have a greater capacitance. The parallel plate capacitor shown here is really the only type of capacitor you'll see in AP Physics B. It consists of two flat parallel plates with a cross-sectional area A and separated a distance d. The capacitance of a parallel plate capacitor is proportional to the cross-sectional area A divided by the separation distance between the plates d. So the larger the cross-sectional area A, the larger the capacitance C. And the closer you bring these plates here by making the separation distance d smaller, the greater the capacitance C. So really, capacitance is only a matter of geometry. When a capacitor is charged, each plate will acquire equal and opposite magnitudes of charge. And hence an electric field, E, is established between the plates. In our problems, we'll assume this electric field is uniform, that is equal in magnitude and constant in direction, hence the equal spacing between the electric field lines. So we're going to neglect the fringing effects that occur at the edges. Because the electric field is constant, the voltage across the plates is given by V equals negative ED. The negative in the expression is only really telling us that as we go in the direction of the electric field, the electric potential drops. Typically in our problems, we'll drop the negative sign. To charge a capacitor, we need to connect it to an external voltage source such as this battery, and the battery maintains a constant voltage V across the capacitor. This is a little capacitor animation lab where we can explore how a capacitor works. We can change the plate area of the capacitors or the separation distance between the two capacitors and see how that affects the plate charges, the electric field lines, the capacitance, and even the stored energy of the capacitor. Let's establish an electric field by increasing the voltage and going from 0 volts to a positive voltage here. And you can see there's electric field lines that are established, and a positive charge Q and negative charge Q accumulates on both plates. We can even bring up a meter that shows the capacitance, the plate charge, and even the stored energy of the capacitor. Furthermore, we can bring in an electric field detector that will actually measure the electric field between these two plates, and you can see it's nice and constant all the way through in that region. As you get out here, then it's 0, but it's a positive 67 volts per meter downwards here. So my question to you right now is, if I were to decrease the distance between these two plates, how would this affect the electric field strength? How would this affect the capacitance C, or the plate charge on either plates, Q, and the stored energy in this capacitor? Take a moment, stop the video, and jot down your answers. Okay, now watch what happens to each of these quantities as I move the separation distance smaller. So D is getting smaller, so as I decrease D, observe what happens. Or you can see here as D is increasing, and look what happens. So once again, as the D gets smaller, the distance between the plates gets smaller. Observe what happens to the electric field, the stored energy, the plate charge, and the capacitance. You should have noticed that all four quantities actually increased as I made the plates get smaller. Why is that so? Let's try to explain this theoretically now. First, we know that in a capacitor, the voltage across the two plates is given by negative E, the electric field strength, times D, the separation between the two plates. The voltage across the two plates is held constant, where the distance between the two plates decreases, and hence the electric field must get stronger. The capacitance of a parallel plate capacitor is directly proportional to the cross-sectional area and inversely proportional to the distance between the two plates. The area is held constant. This is another constant. So, as the distance D gets smaller, the capacitance must increase. And lastly, the capacitance of a capacitor is given as the amount of charge divided by the voltage across the capacitors. Remember that the voltage is constant, and we just learned previously that this capacitance of this capacitor has increased, so the amount of charge that would accumulate on both plates would increase as well. Then we have the stored energy. Hopefully you recall that the stored energy can be calculated several ways. 1/2 times QV, or Q squared over 2 times C, or 1/2 CV squared. Let's take a look at the last equation, because we know that the voltage is constant, and we know that capacitance has increased, so therefore the stored energy must also increase as well. So we saw that as you decrease the distance between the plates, the capacitance, the plate charge, the stored energy, and the electric field all increase. Just to see if you understand this, try changing the area. What do you think would happen if I were to increase the plate area? Here we go. Now take a moment and tell me what would happen if I were to slide this area to a larger area. What happens to the capacitance, the plate charge, the stored energy, and the electric field in that scenario? Take a moment and jot down your answer. Now observe experimentally what happens. You notice that the capacitance, the plate charge, and the stored energy increase, but the electric field remains the same. The electric field didn't change because you weren't changing the distance, and the voltage was remaining the same as well, so E must have stayed the same. The area increased, so hence the capacitance increased. All other quantities were constant. Since the capacitance went up and the voltage was constant, then the charge on the plates must go up. And since the capacitance went up, so was the stored energy as well. Now one more little mini experiment. What would happen if I were to disconnect the battery and then perform the same experiment over? Now take a moment and tell me what would happen if I were to take this separation distance and decrease it, bringing these plates closer. What would happen to the capacitance, the plate charge, the stored energy, and the electric field established between the plates? Do you think you get the same result? Take a moment, think about it carefully, and jot down your answers. Okay, so watch what happens experimentally as I make the distance get closer. D is getting smaller. Oh, interesting. Once again, as d gets smaller, the capacitance increases, the stored energy decreases, yet the plate charge remains the same. Also note that the electric field strength between the two plates never changed. We didn't get the same result as before. Why? Well, the plate charge doesn't change because there's no route. Because the battery is not connected to either plate, there's no route for the charge to be transferred from one plate to another. And it's not going to jump from this gap to this gap, through this gap to this plate. That won't occur. So the charge must remain constant. But what about the voltage? Did that change? Because it's no longer connected to this constant voltage of the battery that it was providing. So let's say if I brought in a voltmeter into this picture. Here's the voltage when the plates are nice and separated from one another. It's 0.67 volts. Now let's decrease the distance between them. Now it's reading 0.43 volts. And now 0.33 volts. So we see that the voltage actually decreases as the plates get closer together. Okay, let's explain this theoretically now. As the distance d decreases, that's going to cause an increase in the capacitance, assuming that these two quantities are constant. Because the charge can't move from the top plate down to the lower plate, that is constant. And since the capacitance increases, therefore it causes a decrease in the voltage across the plates as the distance decreases. Since capacitance is equal to both of these equations, we can write the following, and let's replace the voltage V with negative E times D. Little d is irrelevant when we calculate the electric field. And since the electric field only really depends on the amount of charge per area, which we call the surface charge density, neither of these quantities are changing the charge of the area, and nor this is changing because that's a constant, then the electric field must be constant. And lastly, because the voltage decreases with a constant charge, we can see that that would cause a decrease in the amount of stored energy in the capacitor. So a decrease in the distance d will cause an increase in the capacitance, a decrease in the voltage. The electric field remains constant, but the stored energy will decrease. Okay, one last thing just to test if you really know what you're doing. Let's say if we were to change the plate area. Let's say in this case we decide to decrease the plate area in this scenario. I'd like you to answer what happens to the capacitance, the plate charge, the stored energy, the electric field, and the voltage. Describe what would happen to all of these quantities. Take a moment, jot down your answers, and then let's review the answers. Okay, observe what happens to the quantities up here. So here I am decreasing the area. Once again, as I decrease the area, you'll see that the voltage increases, the electric field increases, the capacitance decreases, the charge remains the same, and the stored energy increases. Okay, the charge remains constant because it can't go from this plate to that plate, jump the gap. Alright, we see that the area has decreased, distances remain constant, so that's going to cause a decrease in the capacitance. Since the capacitance decreases, that's going to cause an increase in the voltage across the plates. Then remember our derivation earlier, our electric field depends on the charge, the area, and this is a constant. Charge is not changing, that's constant. However, in this particular case, the area is getting larger. That's going to cause a decrease in the electric field. Oops, I meant to say the area is actually getting smaller, which is actually an increase in the electric field. And then lastly, we see that the voltage increases and hence the capacitance the stored energy in the capacitor is going to increase. Okay, these are all kind of conceptual questions you should know how to answer from our previous chapter, but we just wanted to reinforce all that. And that's it for our review about capacitors.